right? Okay, let me see. Okay, right. If at any point I'm not audible, please let me know in the chat window, right? Okay. So we are talking about power transmission. So in power transmission, so again, so when you're talking about transmission, we have two means, AC and DC, right? So in DC, it is more or less straightforward, but again in DC transmission is currently employed only at high voltage levels, right? HVDC, it makes only sense at high voltage levels. With respect to AC transmission, right? We have two. One is single phase, and the other is three phase. So single phase connection is used predominantly in distribution network, and it is usually done at lower voltage levels, right? So in single phase, do you guys know what is the single phase voltage in India? What is the standard? Yeah, no, it's actually 230 volt, right? So it's basically the exact. Okay, let me put this. So we actually aspire to be 230 volt, but see, at the end of the day, what happens is that a lot of the way we perceive our in day-to-day aspects is what you call as a residual of whatever British technology and British culture left between, right? So it's usually 220 to 240 volts, and the frequency is 50 hertz, right? So this is again a very Commonwealth thing. You know the concept of Commonwealth, right? So all the countries that were ruled by British. So we tend to, even a lot of things, our bureaucracy, our financial system, our taxation, all those things are the residual of the colonial period, right? So it's 230 volt, but yeah, 220 to 240 is more or less. So then we have three phase, which we use for both distribution and bulk power transmission, right? Okay. So when we're talking about three phase, right, uh, we have basically three phases, right? So one, two, and three. Similarly, two and three. So basically, in three-phase system, we have three coils or three systems which are connected, which can be connected in multiple possibilities. So at the end of the day, if you want to select three terminals and connect them to give you three terminals, there are multiple possibilities, right? So the most common approach is to is two popular approaches are star and delta. Delta is when you actually, so you guys are familiar with the concept of star and delta, right? Good, good. So basically, these are electronic meters. right? So these are the three terminals. And this is R, R dash, Y, Y dash, and B, B dash, right? And here this would be R, Y, B, R dash, Y dash, B dash, and the terminal would be 1, 2, and 3, right? So these are the terminals, right? So this is called as a star winding, or it's also called as a open winding, right? Or it's also called as a series winding, right? And this is called as a closed because we will try to redraw this. If we redraw this, this would be like, and here it would be, right? So it's a closed winding, and since it's parallel, it's also considered shunt, right? So the power level, let's look at the power levels, right? So like when you're dealing with three phases, you have to be careful about what kind of connection it is. So the power would be S is equal to root 3 VL IL, right? And here also S is basically the same. S is, what is this? Can you tell me what S is? Can somebody tell me what S is? All right. Okay. Good. So S is apparent power. Thank you. Thank you. And can you tell me what will be the relationship between V phase? So what is V phase? It is the voltage between these 2 points, right? So this common point is also considered as called as neutral, right? That is V phase, and V line is basically the voltage across this one, right? These two terminals, right? So V phase is equal to VL. What is the factor over here? To X. Here also V phase is equal to VL into Y, right? Just give me 1 second. Yeah. So yeah, V phase is equal to VL into X, and V phase is equal to VL into Y. So can you tell me what would be the values here? X is equal to 1, X is equal to Y is equal to 1 option. X is equal, X greater than 1, Y equal to 1, X, okay, let me put it in, X not 1, X is equal to 1, I have 1, X and Y not 1. And if it is not 1, can you tell me what the value is? What would be the value? Okay, so you guys are okay. This is correct. Okay, okay, good. You guys actually gave me the correct answer. Right. So what will be x? X would be actually 1 by root 3. Okay. X is 1 by root 3. Do we have an eraser over here? You might. Yeah. So x is basically VL into 1 by root 3. That is VL by root 3. And here y is right. And y is 1. Right. So V phase is equal to V line. Right. Similarly, okay. Okay, and so what would be similarly I phase in that way I phase is equal will be equal to I line over here, and here I phase would be IL by root 3, right? So far so good. Are you guys with me? Clear? Okay, I hope you guys are with me. So now let's look at the concept of neutral grounding, right? So what is neutral grounding? So we saw that in star we have an additional terminal along with RYB. Here RYB, we have one more point or one more node which we call as neutral, right? So when we are talking about alternator, right, an alternator is actually connected in a uh, star formation because of two reasons. One reason, first reason being protection, because we can monitor the neutral current for imbalance, and we can also protect the in a phase-wise manner, and also we can take the supply per phase, right? So in order to okay, so basically the purpose of neutral grounding is to provide a closed path for a fault current, so that when you have a grounded fault, see, suppose there is a ground, suppose now there are transmission lines going on from here, right? And now suppose a ground fault occurs, like say a tree branch falls, right? This is ground, right? So between this, there is no closed path. Right now, if you see from the ground, see, suppose from the base, the current is flowing into the ground, and where does it go from here? There is no closed path. So we won't be able to properly detect it, right? So we need a closed path. So to create a closed path, what we do is that we connect neutral to ground, right? So now we have a closed path. So this acts as a closed path. Now we have a closed path, right? So there are different possibilities of neutral grounding. So the first one is just plain or solid grounding. It is called a solid grounding, where we connect the neutral directly to the ground. So this is solid grounding. Now then we have reactance grounding. So where we connect it to the ground via a reactance. So this is called as reactance grounding. And finally, instead of if instead of a reactor, if we use a resistor, right, it is called as resistance grounding, right? So in in a functioning system, we always prefer that alternator be grounded via resistance grounding, right? This will actually provide more. This also actually plays a role in stability, right? Right. Any doubts on this? Okay, I'm assuming if you have any, just let me know, right? Proceeding. Right. So basically, when we are talking about transmission line, there are two major equipments that come into picture. The first one being conductor, and second one being insulator, right? So the point of conductor is that it is to carry current, and the current carrying capacity is proportional to area. What is it? Rho R is equal to rho L by A, and I is equal to P by R. So I will be proportional to A, right? And insulation, the purpose of insulation is to prevent any leakage current between surface of the conductor and the ground. So what happens is that the conductor is at one potential and ground is at zero potential. So there is a potential gradient. And even though air is a very good insulator, what will happen is that if the voltage is sufficiently high, uh, the air in between this can actually break down, right? So that is also the small current, leakage current that is happening like that also is what leads to the capacitance of the transmission line. So an insulation is provided A to protect and also to prevent leakage current, right? Leakage current. And the size of the insulation is actually proportional to voltage. Higher the voltage of the transmission line, higher the amount of insulation that we need to use, right? And when we're talking about insulation, one of the key concepts that we need to consider is the dielectric strength of the material that we use, right? Do you know what is the commonly used materials with which we use the uh, uh, insulators and transmission line for transmission line? Can you guys tell me what it is? Yeah, mica. Good. Mica. It's mica. It's mica. Good. It's mica, right? Good. Okay. So that is about in. So one of the things is that at the end of the day, insulation is not like it's it also will fail, right? So what are the conditions under which insulation fails? So the insulation can fail first due to overheating, right? Can fail due to overheating, which is basically due to overcurrent condition, or could also break due to high electric field intensity, which is due to over voltage, right? Right. So one of the reasons why we connect the stator of the synchronous machine in star manner is to avoid the possible failure of insulation, right? Because in that way, the effective voltage across the phase actually reduces. We saw that, right? It's not actually VL. It is actually V phase VL by root 3. So the effective voltage reduces. So the high field intensity, electric field intensity also reduces, right? So just before we proceed, okay, before we proceed, I'll use this slide to just look at the representation. So when we are representing an alternator, we always represent the voltage as E angle delta, right? Where E is the, this is just before I forget, magnitude of generated voltage, right? And delta is the power angle. Delta is the power angle, right? Delta is the power angle. So where delta is what? It is actually the angle, physical angle, not the physical angle, the electrical angle between rotor, between stator and rotor. I'm measuring the angle that way. It is stator and rotor. So this you probably will learn in electrical machines, right? The real power is P, and the real power depends on delta, right? And reactive power Q depends on P, right? Uh, these are all things that you are familiar with, right? Okay, right. So now let's look at, so this is something that I told you in the introduction session, right? That we kept on trying to push our voltage levels up and up and up. And at some point, we realized that we cannot go beyond a system, right? So high, high voltage systems, right? High voltage system is basically less than 66 kV, right? So it is between the 11 kV line, right? And all the still here. I'm audible, right? I'm audible, right? Yes. Thank you. Thank you very much. All right. So the high voltage system, there is a after a point we cannot use the high voltage system, or there is limitations to high voltage system, right? So let's look at the disadvantages of high voltage transmission, right? So the first reason is, say suppose, let's look at what is S. S is root 3 VL IL, right? So what is the current will be S divided by root 3 VL. Suppose we are actually transmitting 250 MVA or 250 megawatt, 250 MVA power, right, at 13.2 kV, which is 13.2 kV is also voltage level that we use, right? Or say suppose even or 11 kV, right? Basically anything less than 66 kV. What will happen is that it will be, what will be the current? It will be 250 into 10 power 6 divided by root 3 into 13.2 into 10 power 3. Just give me my calculator. Drawing. Right. So can you tell me what the current will be? So basically I can cancel this and put 10 power 3, right? So it is 250 divided by root 3 divided by 13.2, 10.93. Okay. So what we get is 10.93 kilo ampere. 10.93 kilo ampere. And you have to remember I is proportional, higher the current, higher the cross-sectional area required, and higher the cross-sectional area required, higher will be the cost, right? So the first disadvantage is that if we actually are going for HP transmission for higher power capacity, uh, size of conductor will be large, leading to higher cost, right? Second one, we know that power loss. What is P loss? P loss is equal to I square R. So in this case, I is in terms of kiloampere. So this would be in terms of megawatts. So we will end up having megawatt of power losses, right? Approximately, give or take. And which will result in, so due to higher losses, it will result in poor efficiency, right? So the in this whole case, right, this whole issue is coming because of the higher current, right? So how can we actually then okay, so then how can we actually deal with this? So since we know that that S is equal to root 3 VL IL, right? If we want this to be less, we have to increase this, right? So that is where we actually ditch what you call as HV and go for EHV or UHV. Right, we go for EHV or UHV, where this is extra high voltage and this is ultra high voltage, right? So let's look at what are the voltage level. It will be extra high voltage and this will be ultra high voltage, right? So basically 66 to 66, 132 up to 220 is considered as HV, right? So these all are in kV, right? Then we have 400 kV and 765 kV and above. Is considered as UHV, right? Okay, so now let's look at the advantages of EHV, right? So the first one again, let's look at under the same condition that we're looking at a 250 MVA transmission say at 220 kV, right? So what will be IL? Be 250 into 10 power 6 divided by 3 into 220 into 10 power 3, right? Do you know what the value comes around as? Yes, correct. So it will come as 656 amperes. So if we compare this with what we got over here, right, in the for the HV, it was 10.93 kilo amperes, right? So that would be 10.93 kilo amperes money 10.930 amperes, right? Yeah, so you see the difference, right? So that is one of the reasons why we actually go for. Then what will happen? So this will result in the cost of the conductor being reduced, and the I square R losses will come down substantially because the dependence is square, right? Which will result in increased efficiency, right? Okay, now let's look at the some of the disadvantages. So can you tell me what would be the first disadvantage? So now so you see that the cost from a cost of operating point of view, like the operating cost comes down, right? What would be insulation cost will increase? Good, because insulation is proportional to voltage. So since we are increasing voltage, insulation cost increases, right? And second one is circuit breaker cost also, protection cost, the circuit breaker cost also increases, right? So yeah, so that is the advantages and disadvantages, right? So now let's see, I left a plain slide over here. Yeah, I put a plain slide. Okay. So one of the things again, the question is okay, maybe one. Okay. So one thing that we need to ask ourselves is what is the limit up to which we can go, right? So basically, if you look at the power transfer over a line, it is basically like this is a very what you call a simplified equation, right? EV by X equivalent sine delta. Okay, so this is also called as synchronous power transmission, right? So the rule of thumb is that if it is less than or equal to 500 kilometers, if the distance is less than or equal to 500 kilometer, we will use AC transmission. The distance greater than or equal to 500 kilometer, we use HVDC, right? Uh, so what happens is that if you see here, it is the power is actually having a direct proportionality to delta. So to get a huge power transfer for a long transmission line, since XCQ will increase, right? So we will have to maintain a bigger delta, which is not technically easy. So that is one of the reasons we go for HVDC for a long transmission system. And also there is a second reason for using HVDC for long transmission line. Do you know what that is again? Any guess? Varun, there any or Takura, any guess why? So the first reason is stability, right? Second reason is increased reactance. And can you tell me, this is a very obvious but a very important one. Basically is cost. So suppose if you are thinking about a three-phase or AC transmission line, you have physically you need three lines to go, right? But when we are talking about HVDC, you just need one line between the towers. So basically, when you're talking about copper, it just requires 1/3. We use earth as the neutral, but here actually we need three. Here only we need one, right? So for a long transmission system, the cost of conversion somehow becomes marginal, and the cost of AC and DC at that point becomes comparable, or DC becomes more cheaper. So that's why for a long distance transmission line, we tend to use HVDC, right? Does that make sense? So okay. So, but does that mean that we have to go for always go for HVDC when long transmission line? No. In AC also there are like some shortcuts, not shortcuts, some solutions where we use we use like one of the first setup is parallel lines, right? So there will be two R's, two conductors for R's, two conductors for Y, and two conductor for B. So what happens is that since these two are parallel, then XEQ will be halved. Will effectively become half, right? And also the second one is basically introducing series compensation. So what we do is that we introduce capacitors in the line in series, so that also will reduce the effective XEQ, right? So that also can be done. So far, are you guys with me? I hope so. See, if you are having any difficulty, or if you are having any difficulty in following, let me know. Okay? So when we are talking about an EHV line, what usually happens is that there will be a node A, that is a node A, and there will be node B. With respect to EHV line or EHV line, always EHV or UHV always is about transmission, right? So there is a line. There won't be any load or any other nodes in between, right? So the current throughout this line will be same. So which will result in a constant current density. But say suppose when we are talking about distribution system, right? At a voltage level, say suppose when you're talking about 220, you will have one node, you will have one node. So different lines actually say this will be 10 ampere, this will be 5 ampere, this will be 5 ampere, then again this will split, right? This will again split, this will again split, will again split. So effectively at same voltage level, there will be different current density, right? Or different current levels. But with respect to EHV, it will be more or less the uh, same. So between two nodes or for a longer distance, the current density will be same. That is actually one of the better advantages of transmission line operation. So it is having constant current density, right? So if I'm representing it as capital J, which is I by A, where A is the cross-sectional area of the conductor, right? So if the magnitude of the current throughout the length is same, then such lines are known as feeders, right? So EHV lines are considered as feeders, right? And if the current varies, like as we saw in the distribution system, then they are called as distributors, right? Okay, so now let's look again, let's go back to what we were looking at over here. So for selection of cross-section area, right? For selection. So when you're talking about size of conductor, we are actually talking about cross-section area, right? So for selection of cross-section area, we consider only active power, right? Because it is the one that is contributing to the losses, which we are, which is basically heat and the power that we are actually considering. So what is P? It is Pi cos phi, right? Suppose now we are increasing, so this, suppose we have one voltage level, so V1 I1, and this would be cos phi, right? And suppose now we are actually having a different voltage level, say suppose V2, so that would be V2 I2 cos phi. So let's look at the two different same, for same power we have two possibilities, right? Where V2 is n times V1, which makes I2 is equal to I1 by n, right? So basically these two are right. For transmission line, what happens is that uh, I is proportional to A, right? So uh, I1 is proportional to A1 and I2 proportional to A2, right? And we know I1 is equal to I1 by I2 is equal to I1 by N, which implies A2 will be A1 by N. So if the voltage increases N times, the area of cross section decreases by N times, right? Does that make sense? Is that clear? Okay. Similarly, let's see if we are actually what happens to transmission line losses, right? Okay. So P1 is I1 square R1 and P2 is I2 square R2 R2. Transmission lines are different. So what we know is that I2 is I1 by N, right? And we also know A2 is 1 by N A1, right? since R is proportional to 1 by A, right, R2 will become N R1 because the length is not changing in the same material, right? R2 is equal to N R1. So if we substitute this, we will get that the loss will become P1 by N. So even though we may think that since current is getting reduced by N times, the losses does not get actually reduced by N square times. It actually only gets reduced by N times, right? Right? Correct. Okay. So let's look at one question right now over here. One more aspect over here and same loss. Suppose we are having same power, same length, same operation. And one more I missed in the term. This is same loss, right? Same loss, and the voltage is increased by n times. What would happen to area of cross section? Right? Can you guys give it a try, or do you want me to do this one for you? Do you guys want to see how that relationship works out? Or if you want to try it on your own, let me know as yes, or if you want me to explain, let me know as no. Okay, I'll explain. Okay, fine. Right. So suppose that makes this is better, right? Okay. So what we are saying is that there was P amount of power is being transferred, right? And we are say suppose using copper. So we use aluminum, but I suppose for the sake of question, let's consider copper, and we are transmitting it over 200 kilometers, or let's consider as L, right? And say suppose now the initial operating voltage is 11 kV, right? And say suppose the losses is 20 megawatt, not 20 megawatt, you don't have 20 megawatt losses. Say suppose the loss is 2 megawatt or P loss, you consider it as PL, right? Now what happens is that we are increasing the operating voltage by n times, right? So V2 becomes n V1, right? If V2 becomes n V1, and there is this new system, right? So this was the old transmission line, and we have a new transmission line system. So we see, suppose you are a person designing this transmission line, right? So you designed for this condition, but then they came and said, oh no, let's actually make it for n times v1, and they're saying that the power is going to be the same, the material is going to be the same, the length is going to be the same, even actually the losses also is going to be the same. Then what should be the new conductor size that we should choose, right? So let's look at it. We know P is equal to Vi cos phi, and I is equal to, therefore I is equal to P divided by V cos phi, right? And what do we know about loss? Loss is equal to I square R, right? That is also I square into rho L divided by A, right? So what is A? A will become I square rho L by, if I rearrange, the area will be I square rho L divided by P loss, right? And this also will be, if I substitute this over here, it would be P divided by V cos phi P whole square into rho L divided by P loss. Right now, what we're trying to do is that we are trying to create a correlation between what are they asking about area and voltage, considering all the parameters there they are same, right? So in this question, what is given? This is constant. This is constant because same material. This is constant. This is also constant, and this is also constant, right? No, not that is not, the last one is not constant. So this will be A is equal to K divided by V square cos pi square, right? So what we understood is that A is inversely proportional to 1 by V square, right? So A1 by A2 will be V2 by V1 C whole square, which will be n square. So A2 is A1 by n square. So if you are designing the transmission in such a way that same power, same material, same length, and we also want the losses to be the same, then the area of cross section needs to be reduced by n square times. Does that make sense? Okay. What about Dharini and Varun? All right. Good. Okay. This is fine. Now let's look at the next one. Okay. Selection of insulation. Okay. Selection of insulation levels, right? So we have looked at transmission line for some time. Now let's look at insulation, right? So this is based on okay. So when we are designing transmission line, or so far we were looking at whatever we call as VL, V phase, right? When we are mentioning these values, what is actually this? Is it peak value, RMS value, or average value? So we say A, B, so give you a poll. Okay. So far, whenever we are talking about system operation, the transmission line thing, what are we talking about? You should have asked me earlier, but when we are designing for what? Okay, so when we are talking about transmission line, and Varun, what would be your answer? Okay, so yeah, good. So two of you gave B RMS, yes. So when we were talking so far, we are always talking about RMS value, right? But when we are talking about insulation, we are talking about the electric field across this one. And electric field is actually proportional to the instantaneous voltage, right? And we should design it to withstand the maximum voltage or the maximum voltage condition. Uh, so when we're talking about insulation, we tend to talk about the peak voltage, not the RMS voltage, right? So far we have been talking about whenever we say VL or V phase, we are actually thinking about the RMS value. But when we are going to look at insulation, we are actually going to look at um, the peak value, right? And also one more thing that I want you to remember is that in a three-phase, three-wire system, we always tend to say if they don't see any voltage value, it is basically, say suppose they say we have a three-phase three-wire transmission system and the voltage is 220 kV, right? So when they're saying that, it is actually line to line, right? So if they simply say a three-phase three-wire system has a voltage of 220 kV or 11 kV or anything, they are actually meaning line to line RMS, right? Okay. One of the reasons that we need insulators and we saw would cause the failure of insulators is over voltages, right? So in power system there are two possibilities of over voltages. The first one being external and second one being internal, right? What is the external over voltage? Is Do you know what is the source of external over voltage in especially with power system? That's a cloud. That's a lightning. Right, correct. Thank you, Darby. That is lightning. So this is lightning. And here, internal voltage is basically due to switching. So what happens is that when you switch a circuit breaker, uh, due to the nature and timing or the other issues, there might be an over voltage, which is called as an internal over voltage, right? So basically, this lightning over voltage is actually more severe. Is actually more severe than that switching voltage, right? So, so if we actually select the insulation based on lightning over voltages, it is going to be extremely costly, and the chances of actually lightning over voltage happening in the transmission line is relatively less. We also can afford try to do alternate methods of protection against lightning over voltages, but if we go through insulation for lightning over voltages, the cost is going to be extremely high, right? So what we do is that we actually tend to plan for internal over voltages, right? So to deal with lightning or voltages, what we do is that we do something called as a earth line. Do you know what an earth line? Have you guys seen an earth line? Do you know what an earth line is? Okay, cool. Okay, I understand. Okay, fine. That's good. Okay, that actually makes me a little more happy because at least there's something very explicit that I know you are learning today. So what happens is that if next time when you go out and when you look at a big tower, right? You probably have you probably see big transmission towers nearby your home or in nearby locality, right? This is a tower. Pardon my drawing, right? So there would be branches like this, and there will be transmission lines. If you see very closely above the tower, right above the tower, there will be one conductor. So this will be connected from tower to tower, right? Along with all the transmission lines, on the top of the transmission line, there will be a cover line, and this wire is called as earth. Called as a earth wire. So what happens is that even if lightning bolt comes, it will actually, and this line is actually connected to towers. It is actually connected to ground. So if a lightning comes, it actually will hit this line and go to earth instead of coming and hitting our transmission lines and causing over voltages, right? Is that clear, the concept? Right? Okay. So let's look at, see, suppose now you are selecting the 220 insulation for 220 kV, right? You should actually select it for Vmax or V peak, right? Which will be 220 divided by root 3. This is per phase, right? Into Vmax per phase is 220 into root 3 into root 2. So you should select it for 179.6 kilovolt. Right. So this is the, and again you have seen the porcelain insulators, right? There are disc type insulators. We will look at what different types of insulation is. So one rule of the thumb is that one disc is corresponding to 11 kV, right? So next time when you look at a transmission line, just by counting the number of discs, you can determine what the voltage level is. This is just a rule of thumb, right? For your information, right? So this is about insulation. So now when you're talking about conductors, right? Just give me 1 second. So guys, I'm just taking a 2-minute break. Also be back by, I'll be back by 6:40. So if you want to take a break, be back, okay? So I'll be back by 6:40. Yeah, so I'm back. So are you guys all here? I think we'll just wait for Dharani. Is Dharani offline? Wait for 1 minute, then we will continue. Yeah, so I'm going to continue, right? So there are different types of conductors that we use in power system. So the first one is actually solid conductor, or the concept of conductor that we have, where it is like one single cylindrical line drawn out of the material, right? So it will be one single thing. And the standard conductor will be, so if this is A, right, the whole A will be one solid line. Uh, in a standard conductor, what we do is that we use uh, n strands having area A by n. So effectively, when you bundle them, the effective area is A, right? Then there is composite standard yeah, then we have composite standard conductors, where we actually use, instead of using one material, we use multiple materials. We will look at it. And similarly, we also have bundle conductors. So bundle conductors, we tend to use it for more than 400 volt, and this is usually less than or equal to 220 kV, right? Okay. Then, okay. So let's look at the difference between, let's see how the solid and standard conductors vary, right? So if you look at the cross section, it be here, it would be basically, right? Here, if you look at that cross section, right? So it is basically two or more smaller strands. So here, what happens is that here, if the conductivity will be high, and mechanical strength also will be high, right? And you here, usually to get mechanical strength, we twist them. We twist them together for mechanical strength. All right. Mm. One of the bigger problems is that this is actually difficult to transport. So suppose you are building a transmission line, this is actually difficult to transport. This is easy to transport. And so far, except for the transportation part, solid conductor is winning. But one of the bigger reasons why the solid conductor fails is something called as in effect is high, here skin effect, is low. So now that begs the question, what is skin effect? So are you guys familiar with the concept of skin effect? Okay, right. That's fine. That's cool. Probably because you are yet to learn. Okay. So okay, so you probably don't know what's okay. Let's look at what skin effect is. So can you guys tell me? Okay, the skin effect. Okay. So what happens is that when we are transmitting transmitting say current in a DC system, right? When we are transmitting current in a DC system, uh, right? So this is a DC supply. It's not a capacitor. It's DC supply, right? It's a DC supply. So the current and the voltage, the relationship is basically voltage will be constant over time. Or simply put, dV is actually 0. dV by dt is 0, right? Uh, what happens is that in case of AC, uh, since the voltage is varying, there will be magnetic flux linkages, right? And magnetic flux linkages, uh, okay, magnetic flux linkages is actually non-uniform from the center of the conductor towards the surface. So what happens is that the magnetic field is stronger at the center, and as we progress towards out of the conductor, the magnetic this thing will be less. And you know Lenz's law. So what happens is that higher the magnetic flux linkage, it will try to oppose the cause of it. So the resistance faced by the current or the current flow will be higher in the center and less at the surface. So the current will tend to flow through the surface of the conductor rather than through the conductor. So when we are talking about DC, the current distribution is uniform across the cross-sectional area. So if you're talking about a cross-sectional area, the current distribution is basically uniform with respect in a DC system, right? But when we are talking about when we're talking about an AC system, current distribution is not uniform. It tends to be in the surface, and that's so basically like skin of the conductor. That's why it is called as skin effect. Is that clear, Varun? And Sakura, if if it doesn't make sense or what if there is some correction to what I said, please correct me. Also, there's no problem in that. Right? If you want to add something, you can always unmute and tell me. Right? Okay. So when it, effectively what happens is that suppose this is by the physical nature of the transmission line, the resistance that we see is rho L by A. So we will call it as RDC, or this is called as DC resistance or ohmic resistance, right? This is called as E. But when we are talking about AC, so due to skin effect, right, the effective area available for current transfer reduces, right? So basically, A dash is less than A, which will cause RAC to be greater than RBC, right? So by thumb rule, by approximately what we have seen is that RAC is times RDC. And as skin effect, RAC is also proportional to as skin effect increases, RAC increases, right? So basically what we are trying to say here is that even if we are using a big cross-sectional area conductor, due to the inherent nature of AC power flow, we don't get to use that whole area. So it is effectively the waste of an investment. That is why we tend to go for bundle conductor, because as the area reduces, the skin effect also tend to reduce. And so instead of using a single conductor of area A, we tend to use n conductors of area A by n, right? One second. Yeah, sorry about that. Okay, so the rule of thumb is that skin effect is proportional to RAC is inversely proportional to 1 by area, right? Now there is something interesting about the way we actually take stranded conductors. So suppose this is one. So there is a very interesting pattern to the number. So this is one, this is two, three, four, five, six, seven. So if my memory is right, it is going to be 3n minus 2, where n is number of layers. So if there is one more layer, it would be 7 plus, so 3 twos are, okay, this is a 9. So this is, suppose if there are only one layer, so there will be only one conductor. So 3 into 1 minus 2 is 1. So if you have two layers, it is 3 into 2 minus 2. It's not 3 and minus 1. Give me a second, let me just confirm this. Or is it 3 and plus 1? It's 3 and plus 1. I'll confirm this thing. This one I have to confirm. But yeah, there is a rule of thumb for this. Okay, yeah, it's my. It is basically 2 and minus 1. Not 2 and minus 1. Right. Delete all this. Okay. So the way it progress is that first layer will have 1, second layer will have 6, third layer will have 12, fourth layer will have 18. So can you tell me what that, this is a question for you from aptitude. Can you tell me what is the, this is the number of strands, right? Plus etc. Right? What is the, if n is the position, n is the number of layers, right? This is layer 1, layer 2, layer 3. What is the relationship? It is actually 3n plus 1. Am I correct? No. Is it 3n plus 1? So it would be 6 plus 1, 7, correct? And it would be 9 plus 1, 10. No, that is wrong. What is the rule? Can you tell me what the rule is? Pattern is very evident. Okay. I know where I'm making a mistake. Let me see if you guys can help me. So if it is one layer, it is 1. If it is 2 layer, it is 7. If it is 3 layer, it is 18 plus 1, 19. Right? If it is 4 layer, it is 37. So if it is n layer, what will be the relationship? Can you guys tell me? I'll give you a clue. It is basically any guess? Any guess? Okay, think about it and let me know in the next class. Right? Is there a pattern over here? If there is a pattern, what is the pattern? All right. Next thing that I want you to look at is the effective diameter, right? Say suppose, are we yet there? Okay, we are not yet there. Okay, we'll get there. Okay, now let's look at the concept of a composite conductor. So what does a composite conductor mean, right? So one of the bigger problems with using a standard conductor is that the mechanical strength is low, right? So what we do is that we will replace this center strand and replace it with a very strong material and then set this up around it, right? So this would be, so this could be iron and this will be aluminum. So this would be aluminum around it, right? So what will happen is that if you put iron at the center and put aluminum around it, the mechanical strength increases, right? And anyway, one of the bigger reasons is that due to skin effect, the inner aluminum will not be properly utilized. Am I audible? Is there any disturbance? Just let me know if I'm clear. Right? Okay, thank you. So I'm audible. There's no issue. So due to what you call as our the skin effect, the inner aluminum coil or the inner aluminum will not be properly used, right? So if you replace that with aluminum, the effective strength is actually mechanical strength increases. Right? So it is not always usually iron. What we also tend to use is steel. Right? Steel is a very commonly used core. So if we use aluminum conductors with steel core, then we call it as aluminum conductor, steel reinforced. Right? So this is ACSR. Right? Okay. So the way we tend to represent an ACSR line is like we say ACSR. The way we tend to represent ACSR is like ACSR 6 by 1, right? So this means 6 aluminum and 1 steel, right? And one other way of representing is ACSR, another is 30 by 7. So that means 30 aluminum and 7 steel. So the way it will look like is 1, 2, 3, 4, 5, 6, 7. So these all are this all will be steel. Then around it, 2 layers of steel, right? So suppose if every one of them have same diameter, right? Then the effective or overall diameter would be, like say suppose layer 1 will have diameter D, right? Now when we add layer 2, right? So what will be the effective diameter? It will be 3D, right? And layer it will be layer 3, it will be 5D. So yeah, layer 3, if we add one more layer, it would be 5D. So it will just come one more, right? And layer following the pattern, layer n would have 2n minus 1, right? Layer n will have 2n minus 1d. So just going by that, let's look at this one. For an ACSR 6 by 1, right? It means 6 AL strands and 1 PL strand, right? So that means 1 layer of PL and 1 layer of aluminum. That means 2 layers. So effective D would be 2 into 2 minus 1 D. That would be D, right? And ACSR 6 bar 1 is actually used for 11 kV and distribution. 11 kV distribution, right? Okay, this is the first one. Then second one is ACSR 30 bar 7. 30 bar 7 means 2 layers of AL. So you can always look at that progression, right? So it is 1, 6, 12, 18, 24, etc. Right? So these are the number of conductors in each layer, right? So it says 30 bar 7. So it means two layers of aluminum. Means so sorry, two layers of aluminum and two layers of steel. So inside will be steel. So 7 means first layer is 1, then so that is 6 plus 1 is 7. So this is steel. Then they said 30. So there will be 12 plus is 30. So this is aluminum. So basically how many layers? 4 layers. So what is the diameter? It will be 2 into 4 minus 1d. That is 70. Right? I'll just write this one on the top for you guys. Just do this for me. 1, 12, 24, etc. So can you tell me if what would be the effective dia for ACSR 54 by 7? Can you do it and tell me the answer? So you have the pattern on the top and just expand, just find out how many layers of aluminum and how many layers of steel, and find out how many total layers are there and calculate the effective diameter. Okay, so Tarini got 11. What about Takura and Varun? Uh, Varun and Takura, do you guys need help or do you guys need more time? All right. What about Varun? Okay, good. So, okay, even Dani, actually, I think it should come as 90. Let's look at it. All right. So, ACSR 54 by 7. That means 7 steel and 54 aluminum, right? So, 6 plus 1, that is 2 layers of steel. Then 12 plus 18 is 30 plus 24 is 54 aluminum, that is 3 layers. So effectively 3 plus 2, 5 layers, right? So D would be 2 into 5 minus 1 D, that is 90. So, Dharani, the way I think you calculated the number of layers correctly. Probably you did 2 into 5 plus 1, right? So, yeah, this is something that I keep on telling you. It's good to make mistake at this stage because it is a very good reinforcement for you to remember and learn, right? The mistakes that you make right now, you will not repeat in the exam. So, is that clear for you guys, Varun and Takura? Does that make sense now? Okay, good. That's better. Now let's look at the. So now, see, the problem is that we know that physically it is um, again physically we know that it is stranded conductors and all those things. But in our mind, for our ease of calculation, we always want to um, what do you call as have a effective radius and effective diameter, right? So we are going to introduce a mathematical concept over here. That is 1t. Okay, it looks like 2t, but it is 1t. A mathematical concept called as GMR and GMD, right? So this is called as geometric mean radius, right? Geometric mean radius. And this is geometric mean distance, right? So this will make more and more, the relevance actually increases. So this is also called as self distance, and this one is also called as mutual distance. So suppose we want to, this is basically used or predominantly used for calculating inductance and capacitance per phase of a transmission line, because we need this for our representation. If you remember when we were looking at the Y bus or Z bus, we needed the inductance and capacitance, right? So, when we are having a very composite or complex physical implementation of this transmission line, we needed we need to actually deal with this mathematical concept also, right? So this concept is only there for three phase three wire system, right? There is no GMD GMR for single phase system. Single phase one wire system, there is no problem, there is no issue. This whole issue comes only for three phase three wire system, right? Let me just see and do. Okay, so let's look at GMR first. Right. So basically, the definition goes like this. basically this is the effective radius of the conductor measured from the center to the circumference. The effective radius, right? So suppose we are having a conductor. If we are having a conductor, and right. So in a DC system or a proper system, GMR is actually equal to R, right? But then we have the flux linkages. So there will be so effectively we will have a lot of small conductors. Let me see if I can draw the smaller conductors. So this will be the bigger one. Within this one, there will be yeah. So in this case, GMR is equal to R. But suppose we are having considering the skin effect and right, then we will have two levels of inductance. So there will be the L internal and the L external, and effectively the GMR will be R dash, which is actually 0.7788 R, right? So the for any conductor, the GMR is basically for a single conductor, GMR is 0.7788 R. And let's look at GMT, right? So how do we define GMT? Right. So the way we are going to define GMT is it is the equivalent distance of the point K in space, which is usually the center of the bundle, point K in space with respect to other points. It will be actually with respect to other points, other points will be the geometric mean of the individual distances between them. I suppose, okay, the best way to understand this is to look at the diagram. I suppose there is one point in space, which is K. So in our case, it would be the center. Then there is conductor 1, center of conductor 1, center of conductor 2, center of conductor 3, center of conductor 4, center of conductor 5, and center of conductor 6, right? So this is what will be the distance? This will be, it will be 1, 2, 3, 4, 5, 6. So this will be T1K, the distance between the center of middle conductor and this one. This will be T2K. This will be D3K. This will be D4K, and this will be D5K. And last but not least, this will be D6K. So GMT is basically GMT, geometrical mean distance for the point K, is given as nth root of or here it will be sixth root. Okay, nth root of d1k into d2k into d3k, etc. into p and k. This is a mathematical concept. So we are taking the geometric mean, right? Mm, yeah. Right. Is that clear? All right. Maybe when we look at the next setup, it may make a little more sense, right? Let's look at a equilateral system, right? Let's look at a symmetrical or equilateral system, slash system, right? So suppose we have, okay, guys, give me 1 second. Just yeah. So now let's look at a simple three-wire three-phase system, right? So this is a tower, right? And there is the earth line going on the top, right? And we have arranged our three faces such a way that, so this is R, this is Y, and this is B, right? So there is R, Y, and B. Okay, and it is a way that, let me change the color over here a bit. Okay. Such a way that this is an equilateral setup. This may not look like an equilateral setup, but for the current sake of drawing, consider that this is an equilateral setup, right? Okay, where this is, right? This is R, Y, B, and the distance between this is 6 meter, and these two is 6 meter and 6 meter, and the conductor is actually having a radius of 2 centimeter, right? So then we know that the GMR, the geometric mean radius of face R, right, will be 0.7788 into 2 will be equal to, just you can calculate and tell me. Same with GMRY will be same, and GMRB also will be same because they are all having same radius, right? Did you guys calculate? Can you let me know what the values? I can also do that. Okay, okay. That is centimeter. 1.5576 centimeter. So GMR, since we are using the same thing, this is same, right? Now let's look at GMD, right? So GMD is the distance. Okay, let's see. Let's look at the GMD. So let's say GMD for phase R will be, what is the distance of phase R from the next available phase. So this is 6, right? The distance between, so R and B is 6, and the distance between this R and Y is 6. So the effective GMD, the distance for the GMD with respect to phase R is 6. Similarly, GMD for phase Y is also 6, and GMD for phase B is also 6. Therefore, the effective GMD, the GMD of the system will be cube root of 6 into 6 into 6, which is 6. This whole setup worked out and numerically correct because it is a symmetrical system, but this is not actually a practical. This is not how this is a textbook representation. In practice, how it is usually is, there will be R, Y, and B, right? This will be a huge tower, and there will be 3 wires hanging, right? So the distance will be, this is going to be 6 meter. This is going to be 6 meter. This is going to be 6 meter, right? So this is going to be 12. So this is an unsymmetrical system. So if I ask you to say calculate GMD and GMR, can you try? I'll also solve it over here, but I also want you to, okay, I'll give you 1 minute head start and I'll start solving. It's the same way we did right now. Maybe you can try. Okay, here I need to give you one more information. This is RS centimeter, right? So GMR will be, it's same for all line, it will be GMR R, which is whatever we calculated earlier. It is 1.5576 centimeters. All right. Then let's look at GMDR, right? So GMD for the geometric mean distance for phase R. So the distance of phase R from all the other available units, right? That will be, or all the other available lines are 6 into 12. So the distance between this R and Y is 6, R and B is 12. Right? Sorry, B. So this would be, let me put as 6 root 2. Right? Then what would be GMD with respect to phase Y? Would be 6 into 6. That would be 6. And what would be GMD with respect to phase B? Would be again 12 into 6. That would be 6 root 2. So the effective GMD, the total GMD of the system will be cube root of 6 cube into 2. Right? That would be into cube root of 2. Is that clear? What I'll do is I'll give you a chance. we have a let me give you a problem, right? And I want you guys to give it a try. So this is R, this is Y, this is, and let's see. The distance is given as 10 meter, 10 meter, and the radius is given as 3 centimeter. Calculate MD and MR. Please give it a try. So if you need my help, just let me know. Okay? Or if you want to, I'll give you 5. This will take roughly 5 to 10 minutes. Just try solving it and let me know. Okay. Let me start here. I'll just start solving here little by little. EMR is equal to 0.778823 equal to 0.3 equal to the distances root of that meter equal to root of 10. Okay, yeah, I'll solve this and let you know. GMT is not 44.71. Let's look at it. It's 10 meter. And GMT is again 10 into 20. That is equal to 10 root 2, right? So GMT, effective GMT will be cube root of 10 into 10 root 2 into 10 root 2 plus 10 into cube root of 2. That will be 10 into cube root of, so this is 12.599. Yeah, right, that's okay. Then we can cube root, yeah, it's cube root 2, certainly. It's cube root 2 instead of cube root 3, right? Right, Varun, did you get this? Okay, let's just try one more problem, right? One problem. This is not how we actually practically design system, but just to see if you guys are clear with the concept, I'm going to do this, right? So this is R by D. So this distance is 5 meter. This distance is 6 meter. And say suppose this distance is 7 meter, right? And R is say 2 centimeter. 2 centimeter, R is 1 centimeter. Easy calculation. Let me make it easy for you. R is 1 centimeter. Calculate GMT and AMR. Can you give it a try? I want you to try this. You guys got 5.39. Okay. 5.94. Okay, let's see. Let me see. Maybe I did something wrong. Where's my pen? Okay. So, right. GMR. I think there is no confusion about this one. This part is okay. Everybody got consistent answer. Great. 0.7788. Right. So what is GMR or GMDR? That is square root of 55. Right. Then yes, GMDY is square root of 30 and GMDB is right, square root of 42. Right. So basically GMD is cube root of square root of 5 square into 6 square into 7 square. So basically it will be cube root of 5 into 6 into 7, right? So 5 into 6 into 7 is 5 into 6 into 7 is cube root of 210. It is 14.49. What? Maybe I did. Did I do something wrong? I think I did something wrong here, right? Okay, let me see. Square root of 35 into square root of 30 into square root of 42. 210 and cube root of 210 is 5.94. Okay, maybe my this is correct. Cube root of this is okay. I think I don't know how to use a calculator. You guys are correct. It is 5.94 meter. Right. Correct. Good. So you guys are ready with this concept, right? And now let's increase the stakes, right? Earlier, do you remember I told you there is the concept of parallel transmission lines? The concept of parallel transmission lines is that for each phase, we will have two transmission lines. Right, for each phase, we will have two transmission lines. Where this is R1, R2, and there is a distance S, right? This will be Y1, Y2 between a distance S. This is B1, B2, and there is a distance S, and again between them. Right? We have capital. So here each phase actually has its own self GMD. We have to calculate self GMD and self GMR. Here also we have to calculate self GMD, self GMR. Here also we have to calculate self GMD and self GMR, right? Then use this self GMD and then we will have to calculate the GMD of the system. The calculation becomes even a little more trickier. which we will take up in the next class, because we will not be able to cover it right now. We'll take it up in the next class, right? Don't worry, I'm just giving you a taste of what is coming up next, right? So yeah, so shall we stop here? Okay, good. So yeah, just if you have any material, I think I'll try to upload the notes to the share. Do you guys have access to the Google Drive? Do you guys have the access to the Google Drive? Okay, good. So what I'll do is that I will try to upload the notes to Google Drive. Also try to set up few sample questions for you guys to practice. Right? Okay. So see you in the next class. Right? Happy weekend. Right? Chalo. Bye. Right. I'm recording the session now. And let's start. So today we are going to look at the concepts of power transmission, right? Okay, let me see. Okay, right. If at any point I'm not audible, please let me know in the chat window, right? Okay. So we are talking about power transmission. So in power transmission, so again, so when you're talking about transmission, we have two means, AC and DC, right? So in DC it is more or less straightforward, but again in DC transmission is currently employed only at high voltage levels, right? HVDC makes only sense at high voltage levels. With respect to AC transmission, right? We have two. One is single phase, and the other is three phase. So single phase connection is used predominantly in distribution network, and it is usually done at lower voltage levels, right? So in single phase, do you guys know what is the single phase voltage in India? What is the standard? Yeah, no, it's actually 230 volt, right? So it's basically the exact. Okay, let me put this. So we actually aspire to be 230 volt, but see, at the end of the day, what happens is that a lot of the way we perceive our day-to-day aspects is uh, what you call as a residual of whatever British technology and British culture left between, right? So it's usually 220 to 240 volts, and the frequency is 50 hertz, right? So this is again a very Commonwealth thing. You know the concept of Commonwealth, right?